Hello fellow nerds, it's Tim here with a very special treat for you today. So after the previous videos that we did about our air-to-air heat pump heating system, a lot of you were quite interested in the sort of detailed stats that I promised. So this video is going to be all about stats. I've got a very interesting spreadsheet to show you. So yeah, let's get to it. Right, so unlike my previous spreadsheet video, this is not going to be for public consumption, so it's not as tidy, shall we say, as the previous one, not as user-friendly. I've tried to make it as neat as possible, but it's in my own inimitable style, shall we say. So yeah, there's going to be a few things that you may not follow, but I'll try and explain them as carefully as I can. But yeah, so this is basically all of the weather data and heating data over the last couple of months since we were able to start monitoring the heat pump system. So what I've done is I've plugged in the two different outside units to smart plugs. So actually I'm using the GivEnergy smart plugs. I've robbed this one off of our compressor dehumidifier, which is why it's got a little label saying C on it there. And yeah, so I've got two of those, and they're basically plugged in between the wall sockets, the external wall sockets where we're drawing the power from, and the plugs for the two individual outside units. So I'm monitoring both of those individually through the GivEnergy app. And the reason I chose GivEnergy for the smart plugs is because they actually show some nice time series data, and they record the data historically. So you can go back and take that data and add it into your spreadsheet as I've done. So I'll put up a couple of screenshots to show you what the GivEnergy app looks like for some of this data. But basically what I've done is I've recorded the daily values for the kilowatt hours used for each of the external units, and I've added them up together. So what I've done is I've put those in these columns here. So I've got AC1 is the first external unit, and AC2 is the second external unit, and then I've just added those up in this column here called AC total. AC obviously standing for air conditioning, even though we're using these for heating. And then in these other columns, I've got temperature data. Now, what I've actually done is I've found a website. So I'll just show you real quick. This website here called Visual Crossing Weather Data. So I'll put a link to this in the description, but this was one of the best sources of historical weather data that I managed to find on the internet. And all you do is you put in your postcode, and then you set up a date range, and you can view the data and then download it using this tab here, and you just run this query and you download a CSV file. The only limit to this is that you can only download 1,000 days per day, as it were. So you can download 1,000 records per day. Each record is 1 day's worth of weather data. So what I've been doing is I've been going back 2 years at a time, gathering 2 years worth of data, historical data, and gradually adding them to my data set. What I've been able to do is build up 20 years of historical data. So let me show you what that looks like on this tab here. So this is the weather data for the last 20 years for my location where I live. And what I plotted here is the average temperature, but you can see we get a whole load of different metrics. We've got the maximum temperature, the minimum temperature, the average temperature, what it feels like based on things like wind chill and all that other stuff, and a load of other stuff. Just tons and tons of different metrics. One of the interesting ones actually that I spotted here is solar radiation and solar energy, which looks really interesting to me. It doesn't start until, let's see where it goes to. It's only about halfway through. There we go. So it starts roughly 2010, start of 2010. But that could be really interesting to use for, modeling solar generation for my PV arrays that are going to get installed in hopefully in the next maybe 3 weeks, something like that. So we heard the other day, so that's exciting. But yeah, for now, all I'm worrying about is the temperature data. So I've just grabbed the minimum, maximum, and average temperature. And what I've done is I've plotted those along with the heating total kilowatt hours from this column here in this chart here. So you can see the blue columns are the kilowatt hours per day we used for the heating, and the three orange lines here are the three temperature plots. So the thick orange line in the middle, that's the average temperature, and then you've got the maximum and minimum shown around that. So I'm not too worried about the maximum and minimum, I just plotted those for interest, but you can see, generally speaking, so the temperature is on the right-hand axis and the heating is on the left-hand axis, and you can see that as the temperature drops, typically what you see is the heating goes up. That's what you'd expect, obviously. This period here, where we used absolutely loads of energy for our heating, was when it got super cold, and you can see down here it was getting below zero. Let's see if I can hover over. Yeah, there you go. Minus an average temperature of -4 for that particular day, and that's where we experienced the maximum use of nearly 35 kilowatt hours for that day. So while I'm here, you may have noticed that there are a couple of gaps in the heating data just here and a couple of days over here. So these two over here are actually a couple of days where I'd had incomplete data from the GivEnergy smart plugs. I think there was a problem with the GivEnergy servers, so there was a big chunk of data missing from those days. So I've excluded that from this analysis because obviously that would be unrepresentative of the actual usage. So for now, just excluding those. It's not too big a deal because we've got plenty of other days. So this other missing day is when we had the electrician round to add an additional pair of outside wall sockets where we could plug in the two exterior units. So obviously we had the air conditioning heating system turned off for that day so that the electrician could do his work, and we were using the gas instead. So I'll be doing a proper comparison between gas and the heat pump use in a future video, but for now this is just a day that we can't use because obviously we didn't have the heating on. So this is all fine and well, this particular plot, but it's actually not the most useful plot. It's nice for visualizing the data, but from my perspective, a much more useful plot is a scatter plot of, so this is temperature here along the x-axis versus the kilowatt hours used per day for our heating on the y-axis. Now you can see there is a general trend here, as you would expect. The colder it gets, the more energy we use. That is understandable. You can see I've got a few different colors here though, so all of the data that I've got is plotted on here in one form or another, but the red dots are when early on, when we were basically micromanaging the heating, you know, turning rooms off when we weren't in them and then only turning them on when we went back in those rooms and things like that. And we found that not particularly comfortable or effective, so we changed our strategy after that. So I've plotted them here, and you can see that generally speaking they are a little bit lower for a given temperature. They're a little bit lower than the rest of the data points in blue here. And that's fine. That's what we expected, really. So once we move to our sort of more stable strategy of leaving the air conditioning units on for more of the day, just changing the set point temperature slightly, depending on whether we wanted that room a little bit warmer or a little bit cooler. That's what the rest of this data shows, except for 2 points here, the two yellow points, and those were days we weren't in the house. We'd gone to visit family, so we'd set the temperatures quite a bit lower for those 2 days, and you can see they're definitely significantly lower than the rest of the data. So what I'm going to do for the rest of the analysis is only consider these blue dots, basically. But while I'm here, I'm going to mention this very interesting dot up here, which looks like it's an outlier. Even though it was during the period where, you know, the kind of typical running that we've been doing recently, where we have the temperature on sort of a more stable level for most of the day, and I'll explain that one in a bit. But I'm also going to exclude that for the time being, and you'll see why in a minute. So basically, what I've done is in this next plot here, I've stripped out all of the red and all of the yellow dots, plus this little fella up here, and you can see there's quite a good correlation here. There's a nice tight relationship between temperature and energy used, and that means we can do a little bit of basic linear regression. This is where we fit a straight line through these points, basically. This is the simplest model you can do when you're trying to you know, plot a line through a scatter chart like this, and it's not a bad representation in the first instance. You can see the relationship is pretty good. So that's basically what I've done here. Is I've gathered this data from this table over here, stripped out everything that I don't want, and I've put it in this table here. So I've got the average temperature in this column, and then the total heating in this column. Now what you'll see here is another column called DT. Now I'll explain that shortly along with these other two, predicted AC and error versus DT. But for the time being, let's take a look at what this line actually shows in terms of the equation of how you would convert a temperature into an expected heating load. So that's what I've done up here. So that, you can see what there's this formula up in the very, very top left-hand corner there. This line estimate. It's basically, this is just the G-Sheets way of doing a very basic linear regression, and it's comparing the prediction, which is the total heating load on the y-axis and the average temperature on the x-axis, and it's basically calculating what the equation is of this line that fits that best. That's all that's doing. And the two parameters that produces is the slope. So how many degrees, how many kilowatt hours extra do we need for every reduction in degree of temperature? So that's what this means here, minus 1.78 kilowatt hours per degree lower. So that means that if we went from 10 degrees down to 0 degrees, we would use an additional 17.8 kilowatt hours. Basically, that's what that means. And then there's this intercept here, which is just basically where it crosses the y-axis at a temperature of 0 degrees. That's not particularly useful, but it allows us to basically fully describe this line. That's all that does. Right, so with that in mind, what we can now do is we can say, right, okay, let's assume all of these points should lie along this line perfectly, right? If the world was perfect and we had a day of a particular temperature, we could say, right, what do we expect the heating load to be on that day? So let's say 5 degrees. So what we would do is we would go to the x-axis 5 degrees here. We would read up onto the line here and read across to see what that means in terms of the heating load. And just to make that a little bit easier, what I've done is I've stuck a couple of extra columns here along the side to represent that. So this is my what we want in terms of the temperature, and this is what we expect in terms of the heating load. So let's take my example of 5 degrees. Basically, all I've done here is I've taken this equation and I've used it to predict the heating load, and that comes out at 19 kilowatt hours. So we can just take a look here on the chart and read it across, and you can see it's just below 20. So yeah, that looks about right. And what's particularly interesting here is if I've highlighted one particular value of 15.7 degrees C, which is obviously off of the right-hand side of this chart, but that's where this line would cross the x-axis, basically, and that would mean that's where we would need 0 heating, basically. So what that means is any temperature below 15.7 degrees, we would expect to need to heat the house a little bit. That feels about right to me. I suspect we may, not necessarily put the heating on until it's maybe a bit lower than that. But that does sort of, intuitively make a lot of sense. You probably put your heating on somewhere once the outside temperature gets to in the region of 15 degrees. So that all looks reasonable. But yeah, so right, so that's part one of the modelling, shall we say? But let's go back to this delta T, DT, what I call delta T. This is the difference in temperature from one day to the next. So in other words, if the delta T is positive, that means the temperature increased from the previous day to the current day. So what I've done here is I've actually put this weird little fella up here, this strange outlier, I've just added that onto the last row of this particular table, and you can see, let's move it up a little bit, you can see the average temperature on that day was 12.4 degrees. But look at this, the delta T is 9.4 degrees. So the previous day was significantly colder than the temperature on this particular day. Now I can show you this in the, if I scroll back up, it's this one here, right? So the temperature got extremely cold, and then over the course of a couple of days, it just zoomed up really, really fast. So from, where is it? From this day here, the temperature was at 3 degrees, and then it went up to 12.4 degrees the following day, so an increase of 9.4 degrees. But we used loads more energy than we expected to, based on this linear regression here. We used the best part of, well, what's this? Nearly 19 kilowatt hours when we would expect to only use maybe 5 or 6. So what happened there? Well, basically what I think's happening is that there is a lag, which means that if a day is particularly cold and then the following day is much milder, the walls of the house are still cold. So it's still drawing energy out of the air inside the house that you've been heating with our air conditioning heating system, which means that we need more energy to heat the walls than we would have done if the temperature had been more stable from one day to the next. So generally speaking, the temperature doesn't change by 9.4 degrees from one day to the next. You know, look at these values here. It's 2 or 3 degrees at most. You know, somewhere in that ballpark. So the temperature is generally reasonably stable from one day to the next, which means that that's why this particular relationship is very, very strong. I mean, you know, why all of these data points are hugging that line really closely. But there is still a little bit of scatter. You see this fella up here and this one down here, this one down here. Maybe we can actually measure this a little bit. So that's what I've done here. I've taken our delta T value, the temperature difference from one day to the next. I've predicted what we should expect the heat load to be based on this straight line running through the middle here, which is, once again, it's basically just converting the temperature into the heating load using these two parameters, the slope and the intercept, using this equation up in the top left. And I've done that for every single day. And then I've taken a difference between the actual use and the prediction. So basically the vertical distance between each of the dots and the vertical line here. And then I've done a similar plot, a scatter plot, where I plot this delta T value versus the error, the difference in what we expect between what we used and what we expected to use. And that's what I show in this chart here. So yeah, here we go. This is that guy. This is the where we used way more energy than we expected. In fact, we used, let's see how much more than we expected. We used 13 kilowatt hours more than we would have expected to based on the temperature of that day. But the temperature difference was, oh sorry, my mistake. The temperature difference, the temperature difference was 9.4 degrees and we used 13 kilowatt hours extra. But you can see all of the rest of them, all of these other, small errors away from the best fit line there, they also show a little bit of a trend. It's not as strong as this, obviously, but you can see there is a bit of a trend there. And I mean, it's clearly, massively skewed by this guy. But if we exclude that guy, forget that guy's there, you can see that generally speaking, all of these points follow along this line. So I think my theory is basically correct. It's physically reasonable. Let's admit that. In fact, when I used to work for an energy supplier, long time ago now, it was more than 10 years ago. I spent 5.5 years working for an energy supplier, and one of my jobs was to come up with weather models and things like that to help predict and simulate energy demand based on weather data. So this is not necessarily new to me. Just in case you were wondering. So yeah, this is a perfectly reasonable model to assume that there is obviously the main component of heating demand is the temperature on the current day, but an additional sort of second order component is how we call it, would be the temperature difference from one day to the next. So a better model would incorporate that sort of lagged temperature difference. I haven't done that in this particular example because that would be far too complicated. But let's say I'll probably do something along those lines for a future video for those who are super interested in that sort of thing. But yeah, we could go one step further. As I described earlier, we have this solar radiation and solar energy index. which is obviously some sort of measure. I don't know exactly. I'm going to have to look into exactly what this represents, but that's going to be some sort of measure of how sunny the day is, basically. And when it's sunny, we've got very large windows in this house, so we get quite a lot of additional heating from when the sun's out. So that can probably be incorporated as well. So anytime there's extra scatter here, where there's an error in my error, shall we say, it might have something to do with whether or not the sun was out that day. Because if the sun was out, then we would need a little bit less heating load. And if the sun was in, it was a horrible, cloudy, rainy day, we'd probably need slightly more heating load than we would expect. So all of that stuff can be incorporated into a more sophisticated model. Yeah, maybe I will, maybe I won't go into that in a future video. But for now, I think this is the most important thing, really, for us, in that we can say, right, if the day has a particular temperature, we're expecting in the ballpark of a certain amount of heating load based on this best fit line. So what am I going to do with all this information? Well, for the time being, I'm just going to keep an eye on it. I'm going to keep tracking the data and plotting it on this chart. And probably what I'm going to do is include this in a sort of monthly update video. Kat and I are going to do a series of videos called Stats and Chats, something like that. It's a working title at the moment. We may or may not change that. The idea being that we're going to run through our monthly stats for our heating demands, our solar generation, battery usage and all that stuff. And then afterwards we're going to basically just have a little chat about what's been going on in the last month or so, any news and things that have changed and stuff like that. So we're hoping that'll be a sort of monthly thing, and we'll see how it goes basically. The first one will probably be out in another month or so. It's going to be along the lines of the chat we did about our heat pump system that you can see in the previous video in this series. But what I'm also going to do, I'm going to use this data to see whether or not it's worth us changing the tariff that we're on. So I've got another very complicated spreadsheet which I'm keen to show you at some point. Basically, when Octopus announced their Cozy Octopus tariff, it got me thinking, would that actually be better off for us than what we're on now, which is Octopus Go? And it's very interesting. I did some very detailed calculations that I will show you in that spreadsheet. And with all of this weather data, going back 20 years, right, all this stuff, I can now basically, where is it now? Here we go. What I can do is I can plug this into my equation and say, okay, what would our heating load have been over the last 20 years? And I can use all of that data to give me some very nice stable statistics on what our costs would have been under those different tariffs. So that's, I think, going to be extremely interesting. And hopefully, if you're interested in that, you'll stick around for that video coming soon. But for now, if you've made it this far, well done. And thank you very much for watching. And I'll see you in the next video. Bye-bye for now.